Good afternoon, folks. I hope you're doing well and enjoyed your holiday. Since we last visited about regression and the refresh on statistics, I'm joining you today to continue that discussion, and we'll dive into multi-regression, right? And hopefully you've been taking a look at D2L. More of that is being built out. And I'll go through the session today. This will be kind of a two-part. I'm going to break it up in parts because of the size of the videos. So we'll have the content piece, and then I've got some working demonstrations that I'll do too as we kind of navigate the interpretation of the data, right? All right, so let's have some fun. So the way this will work, high-level stuff that I'll go through on D2L, and it won't be a D2L visit every session, but it's since we're kind of getting launched and things to bring to your attention. I'm making videos as necessary, right, to help you in your learning, and there's a YouTube channel out there that I'll post them, and I'll also post in D2L. So use that as a resource in addition to your textbook, okay, and your homework one. I'll spend a little time probably after this session, or maybe in a separate video, discussing homework one, but that is due next Monday at midnight essentially, right? For today, we'll go through linear regression, and we'll talk about multiple regression, more high-level things than anything. And then I'll finish up kind of what we're looking at for ahead for the following Monday and then 2 weeks away. So at least we're kind of can be synchronized. All in all, I would estimate we're probably looking at 40 minutes here, probably another 15 to 20 on the working examples for applied learning, right? But again, these will be broken up into multiple videos. Okay, you will start receiving more updates as things are being loaded or things bring to your attention. I've got some notes that I've kind of put together for you. They're not loaded to D2L yet. Really, the focus was on the stat refresher where we had last class, and just bring up some of those topics. So I've got some stuff that I've had in the past and I'm putting together for you. Not surprising, like I said, it's taken shape. If you go out there and look, you'll see the way that I'll keep track of everything by session, so date, and what files you can have to practice with if you've had a chance. Hope you have, and you could watch these videos and even attend our class and navigate, right? Using either the data analysis package that we talked about last class or the stat tools, right? My preference is the data analysis just because the stat tools, it's expensive, and once you get out of this class after a year, it's, I don't know, your accessibility to it. So either way, log system, if you happen to have very technical questions, obviously you'll get very technical and well-documented feedback and help. If it's rather a simple question, it will be probably answered in 2 or 3 sentences via email. Pardon me. So, okay. So continuing the discussion on linear regression. Last time we talked about the equation, I showed you different relationships, and if we only have 2 variables, then it's essentially a bivariate correlation. And we talked about more as a review. We can have positive relationships right between data points on a line. We can have negative. We can have curvilinear, and we can also have a U-shaped. So there's different patterns that we look at, and we also look at how those data points align with the fit, right? Which is coming up, but essentially linear regression is looking at how two variables move together, how they're correlated, or how they're aligned. And there's really two focuses that we look at on regression. Okay? We look at that alignment factor, and we also look at, is that variable significant that we're saying is possibly associated? We can't always say causality unless we're doing some type of experiment or a controlled environment. So I use association. So is that variable associated? And then if it's significant, we also look at the predictive power. So for forecasting. So those are really two big usages that we're focusing on with regression, right? Okay. It says here, simple linear regression quantifies the relationship. Obviously, that's why we're looking for significance, and we're looking for that coefficient, right? So with simple, we have the intercept, which is coming up, and we also have the coefficient. And we went through this last class as well with, if we have data points, that's the actual data, and then that line, which gets into the least squares, it's trying to fit a line, right? So that's where we use an equation. The computer did it for us, but we do have that equation at our disposal. So the least square estimation, if we were to have, can't really do it on this particular screen, but if we had dots all throughout here, say this was a dot, okay? These residuals and the difference that we have from this line, which they can be positive or negative, lets us understand how much error we have within our data. Okay, so if we have a large points away from this predicted line, it tells us we got a lot of error. It means there's the residual points way out here. Okay, so that's not what we want. So we don't want a lot of error. Hopefully we get a relatively, depends on the data, the observations are relatively close. Okay, you're going to have outliers, and you'll have data points that are kind of one-offs, and that's to be expected. What else I would tell you about this? When we look at a line like this, where it crosses right here, so this would be, we'll say this was like a 5, and say the regression equation was 5 plus 10x. That 5 is the intercept. That tells us the distance from the horizontal axis where it crosses the vertical. Okay, so holding it constant. That's if we had no predictors, just the straight constant by itself, that tells us our starting point. Okay, and obviously the coefficient, so that 10x that I was telling you about, that's our slope, right? So like the 10x, so that means for 1x, that would give us a 15y. So, and that's how we start plotting out this line, right? So y equals, in this hypothetical I'm giving you, y equals 5 plus 10x. Okay, so it's talking about rise over run. If we set, if we have a negative slope, we would see this fitted line go the opposite direction. right? And it could be 5 minus 10x, and we'd see an opposite relationship going. Okay, so it lets us know that the relationship that we're trying to establish by using simple regression is negative in that case versus some type of positive. Okay. Kind of already alluded to this, but residual is that data point, i.e. the observation difference from predicted to what our actual is. Okay. So that fitted line that we calculate, as we get more data points, it can kind of shift it, right? But the residual is that differential. So that's important to know. Okay. This is useful to think conceptually what's going on for establishing our coefficient. Okay, so getting a slope. And if we were to add another variable, we would do that as well. So it gets kind of complicated and tedious. That's why we let the software do it. But if we were to have, this is simple, right? So we have x and y, but if we were to have a third variable, then we would run all through these equations again. Okay. As stated before, we get into a correlation essentially whenever we're talking about just two variables for simple regression. That obviously changes when we get into multiple. And here's our equation for the slope. Historically, I'd run it out on Excel and go through the whole calculation just to prove it out. But since you all have already had an introductory statistics course, and this is an MBA, not necessary at this point. So we'll acknowledge the equation and we'll move on. Okay, so standard error of the estimate. The magnitude of the residuals provide a good indication of how useful a regression line is for predicting y values from x. I did this on purpose. Whenever you see these, there's one slide in here. Whenever you see these are the equation slides, right? So it's kind of bring your attention. And we get a standard error. We summate that, right? So we get a summation of it to kind of get a large number. We have an error term on our formula per se. So normally it's epsilon. And so the equation would be y equals, you've probably seen it as B0 or beta 0 plus beta 1 plus epsilon, right? So that error term, it's measured, but it's inherent, right? So it's a part of the equation, but it's not a value that you will go and plug in per se when you're running your equation, right? It gets calculated in the process. But it's important to know that error term is part of the equation. When we look at some output here shortly, we'll see that, but as far as using it to calculate our observations, it doesn't really factor in as much per se we're going to manually calculate, right? You'll see. Empirical rules for standard deviation can be applied to the standard error of estimate. In general, standard error of estimate indicates the level of accuracy from a regression equation. So that's why I was telling you when we look at those groupings, okay, we are looking as we're preliminary reviewing the data that those observations are relatively close to the line, the majority. And we don't want to see like a annotate on this. If we have a line, we don't want to see a bunch of data points high, then then they shrink and they get really close to the line. That's not good. So we want to see uniformity, is what I'm trying to say. When we start talking about the least square line, that distance, we want to kind of see it standard and uniform throughout. Maybe a couple one-offs, but not some type of funnel per se, not in like a data pattern. Okay. We look at the residuals in Excel. And so that's in our last class, I was kind of showing you that we want them to kind of be relatively consistent. And obviously the smaller or standard error, more predictive, right? There's different rules of thumb, and those are kind of used usefully. We start talking about what's acceptable for standard error. And before I release out rules of thumb, it depends on your field. Like, so for psychometrics, there might be a standard of error that is 0.08, which is acceptable, whereas 0.12 of a standard error on a particular item may be sufficient too. Okay, so we start looking at like variables. That's extra bonus learning, but know that we don't want a lot of error within our estimate. So variation or variance is what we're looking for in the R-squared. This is where student brought up last class the adjusted R-squared. We're kind of going back and forth, and I brought up the adjusted works to penalize variables that are maybe not a good fit with significance. However, most still use the R-squared, but the adjusted R-squared, it's a good indicator for variables that may not be adding much explanation to the variance, right? So what we're looking for with an R-squared is how much of the variance does a predictor, i.e. an independent variable, does it explain of the dependent variable or the y variable, right? So as we have a particular independent predictor, how much does it explain of the variance of the outcome? Okay. And obviously, I know you can see it ranges from 0 to 1. And once we get up to 1, it's perfect correlation. And I brought to your attention, I said, once we get perfect correlation, and one has to question are the variables almost one and the same, right? Not always, but it should make you have a eureka moment of processing of what are the variables, are they that similar, okay? As a rule of thumb, again, using it loosely, a relatively weaker correlation, which it varies by data size, right? Your sample size. 0.2 to 0.3 can be a weak or a strong, just depending on how big your data is. When we start getting into 0.5 to 0.7, that's pretty strong, at least in the social science world. That's pretty strong correlation. Okay. Medium, somewhere between 0.4 to 0.5, 0.6 on correlation. It's a medium correlation. Obviously, when we're talking about these ranges that I'm throwing out at you, we're saying there's significance with that. Okay. So R-squared is a big thing that we're after, and especially regression. Okay. Simple regression, the R-squared between two bidirectional variables is essentially the correlation. Only in simple. Once we get to multiple regression, that is not the case. Okay. I'm going to pause it here for my video length purposes, and then I will pick back up on multiple regression.